Alright, good morning mathematicians. I will be walking through the Unit 3 study guide in preparation for the test on Friday for my odd periods or Monday, lucky ducks, for my even periods, okay? Alright, so the directions say, for problems number 1 through 4, use the diagrams below of the floor plans for a treehouse before and after reduction and enlargement by a copier. So it's important to remember that this is our original treehouse because these questions down here as we go through 1 through 4, they're going to refer to these house floor plans as original, enlarged, and reduced. Okay. So number 1, what is the scale factor from the original design, alright, so this one here, to the enlarged design? Okay, remember that scale factor, I'm sure you're getting really tired of me saying this, but it's important. Scale factor, how we find it, is image, or our new picture, over our pre-image, or our old figure. So if we want to go from the original design to the enlarged design right here is going to be our new figure. Okay, so it looks like we're going to do our ratio that we're going to write is enlarged over original. Okay, you don't have to write this down, but if this helps you, I highly suggest you do it. That way you know which direction or whether your transformation's being an enlargement or it's going to be a reduction. Okay. Alright, so we need to test both sides of these floor plans. So let's do the short sides of the floor plans here. So the enlarged short side is 6 inches. Okay, so that's going to be on top. The original short side is 2 inches. Now 6 over 2, we know that simplifies to 3. So it looks like our scale factor might be 3, but let's just double check the other side really quick. The other side, the long side of our house floor plans are, for the enlarged, the long side is 9, right there. And the long side in the original house plan is 3. 9 divided by 3, or 9 over 3, is the same as 3. So it looks like our scale factor is 3. So we can go ahead and say scale factor is 3. Okay, moving on. Question 2. It says, what is the scale factor from the original design, okay, starting here, to the reduced design, which is over here? So we're transforming our original and shrinking it down. Remember that whenever a reduction happens, our scale factor is always going to be between the numbers 1 and 0, right? That means we're going to have some sort of fraction. I don't want to say like any fraction, because what about like not mixed numbers, but like improper fractions, right? Those technically would still be an enlargement because it's greater than 1. Okay, so in between 0 and 1 is what we consider a reduction or a shrinking of our original plan. Okay, and of course, if you would like to write this down, our new figure, or our image, is going to be the reduced figure, the reduced floor plan, and of course the original will go on the bottom. Image over pre-image. So let's do the short sides first again. So in my reduced image, the short side is 1. It's a little tiny, but hopefully you can see it on your papers. 1 over the short side of the original, which is 2. And that doesn't need to be simplified. If you want to rewrite it as a decimal, that's okay. So it looks like our scale factor is 1/2 or 0.5. And then we're going to check the long sides. Go ahead, the long side of my reduced figure is 1.5. And then the long side of my original is 3. Does it simplify to 0.5? Why, yes, indeed it does. This is the way that I'm going through this right now, you guys, is how I taught you how to do it. Some of you might be saying, "Oh, well, I know to go from 3 to 1.5, I have to divide this by 2, right?" This is good to me too. This is how we find scale factor. You're doing the exact same thing here, except the only thing that I need from you is to change this divide by 2 to a multiplication problem, right? And you should be multiplying. We're going to change this divide by 2, and we're going to change it to multiply by 1/2. Okay, so either way you guys get to your scale factor, I'm fine with. I just need to see your thought process on the paper. Okay, but the way that I taught you is for sure way to get your scale factor. Okay, all right, we are going to move on. We're on question number 3. It says circle the letter of the statement that tells how the area, the area of the enlarged design compares to the area of the original design. Then explain your answer. So, I guess how I'm thinking about this is, well, how does the area of my original treehouse compare to the area of the enlarged treehouse? Well, let's just find the areas really quick. So I'm going to move back up here. To find the areas, we're going to multiply length times width. So it looks like the area of this original treehouse is going to be 6 inches squared. And then we need to compare it to the enlarged treehouse area. So 9 times 6 is 54 inches squared. Okay, now let's take a look at some of our answers. So it says the area of the enlarged design is half of the area of the original. I mean, if this is bigger than this one, if the enlarged treehouse is bigger than the original, that probably won't make sense because we should have more area with larger shapes, so we can definitely get rid of that one. Let's check B. The area of the enlarged design is 3 times the area of the original. Let's ignore this as it shouldn't be there. Is 3 times the area of the original. So let's test that. We said the area of the original is 6, and this is saying 3 times that. 3 times 6 is it 54? No, it's not. It is 18, so we can get rid of B. Alright, how about C? The area of the enlarged design is twice the area of the original. Well, is 6 times 2 54? No, it's not. By process of elimination, which is a great test-taking strategy, it looks like our answer is D, but let's just double check and make sure. It says the area of the enlarged design is 9 times the area of the original. Well, is 6 times 9 54? Yes, it is. Alright, so now we need to explain our choice, right? And what you could say is, I found the areas of the original and enlarged I found the areas of the original and enlarged, and then honestly you could just say D is the only one that was true. D was the only option that was true. Okay, so I honestly, you guys, I just need to see what your thought process was. Did you find the areas? Did you compare them? And then did you test anything? Okay, that's what I want from your explanation. Now we're going to take a look at number 4. Okay, it says circle the letter of the statement that tells how the perimeter of the reduced design, okay, so now we're talking about perimeter of my smaller figure up here, compares to the perimeter of the original design, and then explain your answer. Do not forget to explain, please. Okay, so really quick, let's, if you guys check out, what lesson was it? Yes, if you check out lesson 2.3 in your guided notes, and it was in the summary section on page 18. Here you'll find some rules just about how shapes relate to each other in regards to scale factor. Okay? So let's go ahead and read some of these. It says the perimeter of the reduced design is 1/2 of the perimeter of the original. We're talking about perimeter here, but first we probably need to find the perimeters. Let's find the perimeters first. So of the small or reduced treehouse floor plan, we have 1.5 plus another 1.5 plus 1 and 1. 1.5 and 1.5, this is 3. And then 1 plus 1 is 2, 3 plus 2 is 5. So the perimeter of this reduced floor plan is 5. Let's find this one really quick. 3 plus 3 is 6, 2 plus 2 is 4, and that's going to be 10. So immediately you should probably be able to compare these two, 10 and 5. The perimeter of the reduced design is 1/2 of the perimeter of the original. If that is the first one you read, kudos to you, and that is actually the correct answer. Okay, so again, here you could say for your explanation, sorry, you couldn't see that. For our explanation, you could say I found the perimeters of the original and reduced, and then option F was the only option that was true. F was the only option that was true. Okay, so nothing too fancy here. But if you take a look, going back to what I wrote up here, if you took a look at lesson 2.3 on page 18, you would have come across a rule that says the perimeter of your image or your new figure is equal to the scale factor times the perimeter of your pre-image. So if we took this equation that we gave you guys and we just found out what the scale factor was, well, we wrote down the scale factor from the original to the reduced, which was 0.5. Oops, I forgot to write this officially and box it so I know that's my answer. Okay, so we said that the scale factor was 0.5. So the only we know that we need to multiply the perimeter by 1/2. And just briefly skimming over these options, 1/2, F is the only one that has 1/2. F is the only option that has 1/2 as its scale factor. So if you would have used this and then circled F, that's a much quicker way, but it's not the only way. Okay, so either way I am fine with. All right, we're going to continue on. We're going on to the back page over here. So it says the two polygons below are similar. Solve for x and y. Let's find where x and y are first. Looks like x is right here, and then I'm going to switch colors, and y is over here. Okay, so we're going to be using scale factors again. So let's solve for x. Let's first find out what the scale factor is. So really quick, let's go ahead and compare this side DC to this side 4.5. So I'm going to treat this bigger figure as my image and this smaller figure as my pre-image. So when I write my scale factor ratio, it's going to be 6 over 4.5. And I'm going to get out my trusty calculator. Okay, and we're going to see what that equals. 6 divided by 4.5, it's 1.333333. I don't know if I like that. Let's see if we can. Actually, what I'm going to do is I'm going to find the scale factor going from this going from the bigger to the smaller. So I'm going to get, I'm actually just going to flip these two. So let's try this again. Scale factor, we'll do 4.5 over 6. Let's see if we get a nicer number. So 4.5 divided by 6. I like that much better. And this is equal to 0.75. So it looks like our scale factor going from the bigger shape to the smaller shape is going to give me, I'm sorry, I lost my train of thought. The scale factor going from the bigger figure to the smaller figure is 0.75. Okay, that is the first thing that we needed to find in order to help us find x and y. So let's take a look. Which side corresponds with x in the big figure? Oh, well, that's 5. So remember, whenever you apply the scale factor, you just need to multiply. So in order to find x, so x is equal to, right, this length over here is equal to 5, which is my corresponding side, times my scale factor, which we said was 0.75. And we're going to type that into our calculator here. 5 times 0.75 is equal to 3.75. And that is what x equals. To check your work really quick, let's do 3.75 divided by 5. Does it equal 0.75? Yes, it does. Okay. We're not done yet. We need to solve for y. So, okay, let's put this here. So y is equal to actually, because we're starting here, because y is over here in the large figure, we're going to do something very similar to this equation we set up here. Okay, so in order to get 3 over here, which is the corresponding side to y, we multiplied some number y times 0.75 in order to get 3. Okay, so we kind of have to move backwards here. So how can you use these two numbers, 3 and 0.75, in order to find y? Well, hopefully you guys remember that we should divide by 0.75 in order to undo this multiplication. Okay, and so when you divide 3 by 0.75, when you type it into your calculator, you should get 4. So y is equal to 4, and that is your second answer. Let's just double check that really quick. Is 4 divided by 3, whoops, I'm sorry, I did that backwards. Is 3 divided by 4 equal to 0.75? Why, yes it is. And there you go. Okay, moving right along. Number 6, we are revisiting some coordinate rules. So it says, tell whether the rule for each backpack below would be similar to Mug's original XY. So here we're not having you guys actually draw any backpacks. We're just giving you rules, and you're supposed to be able to tell us whether or not they are similar, or whether or not they create similar shapes. So I think what's important is, well, what defines a similar shape? Well, a similar shape, similar shapes are the same shape but the main difference is that they are different sizes. Okay, so it's important to remember this. They are different sizes. They're the same shape, but they are different sizes. Okay, so if you look back to, I think in lesson, yeah, it's lesson 2.1, So lesson 2.1 and 2.2, where you can find these coordinate rules. Okay. What happens when we add 3 to x and subtract 3 from y? Well, if you remember, when we add 3 to x, we move 3 to the right, and when we subtract from y, we move down, and then we move down 3. Okay, so this is what's happening with this coordinate rule right here, x plus 3 and y minus 3. But the question is asking us to write yes or no and then explain why. Well, did we change the size here? No, we're just moving it, right? So it's the same shape, they're just in different positions. So can we say that they are similar? Read this up here. Similar shapes are the same shape, but they are different sizes. They must be different sizes. So we say no. They are not similar because they are the same size. Okay, next one. What's happening to the coordinates now? Well, hopefully you said that we're multiplying each coordinate by 5/4. Okay, so when you multiply the x and y coordinates by the same number, can you conclude that the shapes are similar? Yes, we can. When x and y are multiplied, and that's important, multiplied by the same number, put an emphasis on that, the shapes are similar. Okay, we are almost done here. Last one. What operation is what is happening to x and y? Are they being multiplied by the same number? Yes. Yes, they are. And you would, of course, write your explanation why. Okay? Alright. Moving on. We are on number 7 now. We have 2 parallelograms here, and they tell us that they are similar. Excellent. That kind of saves us a lot of time. So it says, find the length of side AB, which is this side over here, and then the measure of angle R, which is this angle right there. So really quick, we should recall information about angles of similar shapes. Well, what do we know? We know that the corresponding angles are the same. They don't change. So this angle A is the same as angle Q, B is the same as angle R, and so on and so forth. But what you should remember is that this angle and the angle that is consecutive to it, right? Consecutive angles we said were supplementary. So 73 plus this angle should equal 180 degrees. So to find angle R, we should subtract 180 minus 73. That's your calculator. And that is 107 degrees. And that is the measure of angle R. Okay. For side AB, we should definitely use some scale factors here. So if we, scale factors or adjacent side ratios, whichever you like. Actually, let's do the adjacent side ratio. So in QRST, it looks like our adjacent side ratios is 6/2, which is the same as 3. So then the adjacent side ratio, which is this side over 5, I'll say this is y here. So y over 5 should also equal 3. Well, what number divided by 5 equals 3? Think about it for a second, and when you're ready, write the answer. So side AB is equal to 15. So we have AB as 15 and angle R as 107. Alright, last type of problem that you will see on the test, this shadow problem, and then this bonus problem over here. We're going to tackle the shadow problem really quick. So the reason why these shadow problems work is because these two triangles that are created, these pink lines are imaginary lines. They're similar. These two triangles that are created are similar triangles, and we can use all of the tools that we've used before, such as scale factor, adjacent side ratios, and all of that good stuff, and apply it here in this new context. So let's continue our use of adjacent side ratios. But first, we need to read the question. It says, use the, sorry you can't see that, use the diagram below to determine the height of the flagpole. So the height of the flagpole is over on the left side over here, so I'm going to call that H. H is for height. Now, let's write the adjacent side ratio of, let's do shadow over height. I like that. Shadow over height for each triangle. Right, so for the little triangle, I'm going to write it below. Shadow over height, well, the shadow is 2.5 feet, and then the height is 4.5 feet. Okay, and then the shadow of the large triangle here, sorry, you can't really see that. The large triangle over here is 12.5 feet, and the height, of course, we do not know. And we know that these two values, whatever, these two fractions, I guess if you can call them fractions, have to be equivalent. They have to be the same. So let's see what happens when we divide 2.5 by 4.5. So 2.5 divided by 4.5 is 0.5555555 forever. So this may not be the nicest of numbers, and that's okay. But let's try a different way. Let's see if I can think about this. I need to go from 2.5, and I need to multiply by some number, which I don't know, in order to get 12.5. How am I going to solve for this number? Well, all we need to do really is just divide 12.5 by 2.5, and we got, look at that, and we got 5. That is a much nicer number than 0.5555555. Okay, so we're going to multiply this. We're going to multiply this number by 5 to get 12.5. Let's test it really quick just to be sure. 2.5 times 5 is 12.5. Excellent. So this means you should be able to do the same exact thing for 4.5. You're going to multiply it by 5 in order to get H. And we are almost done. 4.5 times 5 gives me 22.5. So the height of the flagpole is 22.5 feet. Excellent. Okay. Last one, and this is the bonus question. Unfortunately, you will not get extra credit on the homework assignment, but I encourage you to try this because I want you to at least try to solve the bonus question if you have time, okay? So here we have those nested triangles, or those triangles within triangles, okay? So it will probably help to draw two different triangles, very similar to like the problem number 8. It's easier for us to visualize when there are two separate triangles. So here's one where the submarine is 60 meters, okay, and then the I guess, what do I call that? It's not height now, it's depth. I'm just going to call it depth. So the depth of the submarine is 35, okay. Then we have, oh no, the lights are turning off. Then we have the larger triangle on the other side. There we go. Larger triangle on the other side, not on the other side, but just kind of expanding all the way over to the other side is what I meant to say. And it looks something like this. You don't need to draw it exactly the same size, just know that it's much bigger. Okay, so we want to find this depth over here, which is labeled x. Okay, and then notice how the triangle continues all the way up to the ocean surface. Yeah, it does not stop here. It does not stop here, which is, I know, very tempting to say that this length of this leg of this triangle is only 150, but we must go all the way back to the ocean surface. So instead, we're going to have 150 plus 60, which is 210 meters. And now we have, oh no, the bell rang. And now we have some dimensions to work with. Okay. So let's find the scale factor from the small to the big. So scale factor is, of course, image over pre-image. So we're going to write 210, which is our new figure, over 60, which is our old. Let's type that in really quick. 210 divided by 60 is equal to 3.5. So similarly, when you write the ratio for the other side, when you write x over 35, it should equal 3.5. So in order to solve for x, which is a number we don't know, we should multiply 3.5 times 35. So let's go ahead and do that. 3.5 times 35 is equal to, so in this case, x, the depth of, I don't know what to call this, maybe it's like an underwater cave or an underwater cliff, is at 122.5 meters. And that is your answer. Alright, so please come see me during Bobcat. Please come see me sometime before the test, because I will not be able to help you on the day of the test. Alright? Well, happy studying.